Hello, I'm Yonatan, your host for Rocket Talk, a Project Essence production. Project Essence consists of over 20 members from all around the globe. While we have not much in common with each other, we share a common love of science and space exploration. I am joined by Byong.
Hello.
Peter.
Hello.
And Bartek.
Hi there.
We have a special guest today. You might know him. This is Christian Reddy from Launchpad Astronomy.
Hello, thanks for having me.
Mr. Reddy, can you give us a quick introduction to yourself?
Well, sure. My name is Christian Reddy. I'm an astronomer. I've actually been working as a professional astronomer in some capacity since I was 13 years old, which is kind of a funny story. I also had a chance to work on the Hubble Space Telescope for a few years. I guess that would be my claim to fame, so to speak. And today I am a professor of astronomy at Towson University in Maryland. So I have a little project on the side called Launchpad Astronomy, which is my personal outreach efforts.
That's a track record if I ever saw one.
Thank you.
I mean, that is like more than all of us put together.
Well, it's been a long, strange trip, but I'm glad I've been on it.
All right, glad to have you on.
Thank you.
Anyway, first order of business for this podcast is, you've probably heard of it, the Raptor test fire a few days ago. So what happened? So a couple of days ago, Elon Musk decided to post a couple of tweets about his new hobby, testing rockets, over the weekend.
That's a nice hobby.
Oh, it is. I bet.
I wish I had one like that.
I mean, seriously, that guy is playing Kerbal Space Program in real life.
Yes, but let's not fall again into the same thing we did last week, to making KSP commercials. Let's move on.
Yeah, that's true.
Okay, so the Raptor engine, for those of you who don't know, is the engine meant to power the Starship Super Heavy, formerly known as the BFR, the spaceship that is supposed to take SpaceX to Mars and low Earth orbit and the Moon and many other places. It's a crazy powerful engine. It's using liquid methane and liquid oxygen as its fuel. And they had a major redesign of the engine. And the news is the first test fires of the new design.
So what was the design change from the old one?
We're not quite sure yet. I don't think there's any information about the redesign itself. There was rumors of a double cone nozzle, but that was just because of the placeholder and something that was not really attached there. So that's not actually the case. So we don't know yet.
Okay, and then so this Raptor flight engine. So the engine burn test. I haven't been, just to put it this way, I haven't been following about spacecraft engine for a while. And what are they exactly testing on these engine burn tests? Is it like how long could the engines go, or is it how much thrust it could produce?
Both. They're testing everything in the engine to make sure that everything is completely nominal before they fly the engine. Seems like we've lost Peter.
Oh, and he's back.
Yes.
So sorry. The power just cut out. The thing is that I feel like everything is trying to defeat our purpose. I don't get it.
Yeah, the next thing we're going to have a massive coronal solar ejection, and the internet will die.
Right, as we just attempt to upload this video.
A massive solar flare fries everything. So, could anyone tell us more about the rocket test?
So the latest news we got from Elon was that they reached 172 tons of thrust, which is above the 170 tons which is the minimum they need to use it on the final spaceship. But actually, they're hoping to achieve something like 200 tons in the first version, and the next version is supposed to even achieve 250 tons of thrust, which is amazing.
Of course, this is Elon Musk making the promises, so we don't know everything. So we don't know whether or not that will happen.
Yeah, we also were supposed to have crossfeed in the Falcon Heavy, but that didn't happen. But still, it's the most powerful rocket today.
And he does deliver his stuff, but
Agreed.
at a delayed rate, that is.
All right. The second interesting news bulletin that we're going to cover is the discovery of a new dwarf galaxy. Mr. Reddy, as an astronomer, he can give us the full import of this discovery.
Oh, well, thank you. Yeah, so it looks like there's a team of astronomers who were using the Hubble Space Telescope in an effort to study a foreground cluster of stars called a globular cluster. The interesting thing about globular clusters is, they are collections of old stars, and by understanding the oldest of the old stars in the cluster, you can learn a lot about how stars evolve, how long the stars have been there for, and therefore how old the universe is. Well, while they were doing their work, they discovered there was a fainter group of stars lurking behind the cluster, and they quickly realized that this was, in fact, a background galaxy. So this galaxy is not the kind of spiral, beautiful, gorgeous, grand design galaxy that we are familiar with, but rather it's a type of galaxy called a small dwarf spheroidal galaxy. And these dwarf spheroidal galaxies are kind of like the building blocks of the universe, because early in the universe's history, these small dwarfs would combine together to build up the large spiral galaxies that we see today. So whenever you get to see one of these dwarf spheroid galaxies by themselves, you've got a kind of a pristine fossil record of the universe's earliest days.
Christian, I'm intrigued. How does the mechanics of such a spheroidal galaxy works?
The mechanics of a spheroidal galaxy? How does it work? Well,
yes.
Yeah. Well, like anything else, every galaxy, and indeed every structure of the universe, all the way down to even a small asteroid, is sculpted by gravity. So when you have a situation like a dwarf spheroid, you have essentially a loose collection of stars that are held together by mutual gravity. Now, that would imply that there's something big holding it together. And indeed, in large galaxies like our Milky Way, there are some very large things that are, well, helping to hold the galaxy together, and those would be supermassive black holes. In the case of a dwarf spheroid, however, it's really just the mutual gravitation of the stars themselves. So the stars are kind of swarming around as almost kind of like a very slowly moving beehive, you might say, where each star is a bee.
Interesting. So you can call yourself a archaeologist studying the amber space, which contains within itself the bees millions of years old.
I guess so. Dwarf spheroids are those little tiny bits of fluff that build up the universe.
Yeah.
So, is this galaxy, is it a satellite galaxy? Is it separate?
Well, it's not yet 100% clear, but the galaxy does appear to be about a little over 2 million light years from a nearby large spiral galaxy. Both this dwarf galaxy and the large spiral galaxy are both located in the constellation Pavo. Pavo is not visible from the northern hemisphere. You have to go down to the southern hemisphere in order to see it. But the two galaxies both appear to be part of what's called the Pavo group of galaxies. So you could think of it as like a small collection of galaxies. So because you have this really large galaxy, which I believe is called NGC 6744, if you have this small galaxy next to this big, large spiral, the question then comes up, are we looking at a satellite galaxy? And the answer is we really don't know. It's very likely that what we are in fact seeing is a standalone dwarf, which is perfectly fine and certainly allowed in terms of laws of physics. But what might happen maybe sometime deep into the future, perhaps those two galaxies will interact. And by interact, I mean to say maybe the large galaxy NGC 6744 will absorb or swallow the newly discovered dwarf.
You said the distance between them is 2 million light years. Can you put that in some sort of scale?
Well, sure. That's roughly the same distance between the Milky Way galaxy and the largest spiral galaxy to the Milky Way, which is the Andromeda galaxy. So the Milky Way and the Andromeda galaxy are the two large dominant members of our local group of galaxies. So, that's roughly the same distance that we're talking about between these two galaxies, or roughly as far apart as we are from Andromeda.
That's pretty far away.
But that's also relatively close in terms of, that is very far away, but that's also a stone's throw across the universe. It's always a relative scale.
Yes. I was just wondering, has there been a set distance at which a dwarf galaxy interacts with a larger galaxy to form, like how to become what's the word, an orbiting dwarf, I guess. Satellite, yes.
How to become a satellite galaxy. Well, the thing is that gravity is something that can literally work across a virtually limitless distance. So it's possible, although this hasn't yet to be measured, but it's possible that this new small galaxy, which is called Bedin 1, may be under the gravitational influence of the larger spiral. So it may be that eventually it's slowly moving toward this large galaxy. So to answer your question, what is the cutoff point? At which point does it become gravitationally bound? That would be when its motion is changed from what would otherwise be a straight line into a curved, bent orbit where it eventually comes around and completes a full circle. So what that actual distance is really depends on the masses in question. We know that, for example, we have satellites to the Milky Way galaxy that easily extend out to several 100,000 light years and possibly as far as 1 million light years, and they're still gravitationally tethered to the Milky Way. Maybe that's what we're going to see here in a few 100 million years.
So I have two more questions. One was, what is the origin of the name Bedin 1? And two, is there some sort of an analogy to the Roche limit for galaxies?
Well, sure. The galaxy's name came from the last name of its discoverer. So astronomy is really done, modern astronomy, I should say, is done with not just an astronomer, but a team of astronomers. And so you always have a lead astronomer on every research project called the principal investigator. Well, the principal investigator of this particular project is Dr. Luigi Bedin, and therefore the galaxy is named Bedin 1 after him. So if he should get lucky enough and discover another galaxy, that'll be called Bedin 2. As far as a Roche limit for galaxies, I'm not 100% familiar with the specific dynamics. So the whole dynamics of galaxies and how they interact is an incredibly rich area of study unto itself. So I don't think galaxies have what we think of as a traditional Roche limit, but there is a distance at which the less massive, or actually both galaxies, if they're roughly the same mass, will begin to tidally distort each other. In other words, they'll cease being traditional spiral galaxies and they will start to extend into a stream of stars. Exactly where that actually occurs in terms of physical distance depends entirely on the masses of the two galaxies. So we could expect a situation where if Bedin 1 travels too close to NGC 6744, that the larger galaxies tidal forces acting on the small galaxy will change the shape of that small galaxy from a dwarf spheroid and stretch it out into a stream of stars. Exactly where that occurs, however, it's not quite clear. It depends all depends on the mass. But to an order of magnitude, I would say probably within a few tens of thousands
That
of light
seems
years.
relatively close to the 2 million light years you just mentioned.
Yes. Mhm. It also depends on how compact the Dwarf Galaxy really is. So far, we think it's somewhere around 3,000 light years across, which is pretty compact.
That's like almost a thousandth of the Milky Way, isn't it?
Yeah, that's right. About 1,000th the diameter of the Milky Way. Milky Way is about 100,000 light years across.
Wait, I think I had another question and I forgot it. Have we ever discovered a rogue star outside of a galaxy?
I believe the answer is yes. There have been some stars, or there are some stars rather, that appear to be at distances that place them outside of the Milky Way. And it kind of makes sense because stars should they maybe swing too close to a supermassive black hole or a dense collection of stars, if they approach at just the right velocity, there's a chance that they could be ejected out of the galaxy. And so my understanding is that a few such stars have been detected. I'm not sure which ones, though.
It is important to remember that the galactic expanse between galaxies is not completely devoid of every atom. There's stuff there, but it's at such low densities, it is completely negligible.
Pretty much, yeah, that's right. And we're also forgetting the situation with dark matter, this mysterious substance that does not seem to interact with anything, but exerts a gravitational pull. And as far as we can tell, that dark matter dominates the universe. It's there, even when nothing else appears to be. We think our universe is about, we think that all the matter that you and I can see, even the most tenuous, diffuse trace of gas, amounts to less than 5% of the mass of the universe.
What is this? How much do we know about the dark matters?
Well, not very much. That's why we call it dark. It's that's always the excuse that's always the name rather that astronomers give something that we don't know. Well, we don't know what it is, but it's dark. Here's what we do know. We know that it exerts a gravitational pull. We know that it is everywhere. And we also know that it is what's called weakly interacting. And that's just a fancy way of saying that it can pass through ordinary matter. So you wouldn't expect to find a star made of dark matter. You won't expect to find a planet made of dark matter because it doesn't clump together. It's weakly interacting. It passes through itself and everything in between. But one thing that we have been able to determine pretty convincingly is that it's everywhere.
So if it's everywhere, like it could be in our own solar system.
Yes, there's probably a speck of dark matter passing right through your room right now.
And since it passes through everything, it could be passing through me and everything around it.
Absolutely. Yeah, I mean we deal with particles that are weakly interacting all the time. A very famous example are an interesting little particle called a neutrino. Yeah, exactly, right. So the whole idea is that neutrinos emit from the sun. They're also generated in supernova explosions, and there's something like 100 million neutrinos passing through your body every second.
Oh, wow.
Kind of creepy if you know it.
No.
I think it would have been better off if I didn't know these things before I go to sleep.
A new existential crisis.
If you want to view it that way, sure.
I must say, the difference between dark matter and dark energy surely can't be that much because technically matter can convert into energy, energy convert into matter. So wouldn't they have very similar properties?
Well, yes, you're right. There is that relationship between energy and matter given by Einstein's famous equation, E equals mc squared. So now the question is, well, just because dark matter and dark energy both share the moniker dark, remember, dark is what we call something when we don't yet know what it is. So it isn't to say that dark matter can convert to dark energy. I mean, I guess, what we're really talking about when we talk about dark energy is almost a completely different phenomena than traditional energy. It's the energy of vacuum space itself, where particles can create each other as particle and antiparticle pairs, and in so doing can drive the expansion of the universe, or rather can accelerate the expansion of the universe. Now I'm really hand waving over this, so pardon my oversimplifying things, but the idea is that dark energy is we understand how energy can be created even from a vacuum, but what we don't really understand is exactly what the source of precisely both what the source and the nature of this energy is and how it results in this accelerated expansion of the universe. So that's the dark part.
Oh, okay. That really clears things up, because I always carry that misconception in my mind.
Right, yeah. They're not quite the same thing. They're just two things that are very fundamental about the universe that we don't fully understand yet.
Okay.
But that's okay. That's why we like to do science.
Right.
Going back to that study about dark energy and dark matter, does it say that instead of having dark matter embedded into galaxies, making them spin faster? Because from what I understand, that's how dark matter was discovered in the first place. Does it kind of squeeze the galaxies from the outside?
Well, in a way, I mean, it does. You're right. It does produce dark matter. Let's be clear about which dark we're talking about. But dark matter does appear to add much more mass to the galaxies than we can actually see. And you're right. Galaxies should, spiral themselves away a little bit, or there should be more stars being flung out into space. If you do all the numbers and then you only find that there's only a handful of stars that get flung out into space, what's going on here? Yeah, you're right. That dark matter seems to be accounting for the extra added mass the galaxies all seem to have. Something else about the rotation of galaxies that's kind of curious, and this maybe speaks more to your point about how it was discovered. If you think about how the planets all orbit the sun, the farther away you get from the sun, the slower the planet moves. Well, you would expect the same thing to happen in a galaxy. You'd expect the farther away you get from the center of the galaxy, the slower the stars should move. And instead, it's not the opposite, but the stars don't really slow down. The galaxy rotates almost as if though it were a solid disk, suggesting that there's a lot more mass there than what we're able to see. And so we call that mass dark matter.
But why doesn't it affect the solar system itself, like planetary bodies?
Well, the one thing about dark matter is that it only seems to have an effect on very large size scales. So our solar system is simply too small for dark matter to play any kind of observable role. It's not to say it doesn't exist in our solar system. It's not to say that it doesn't play some teeny tiny role, but until you get to galactic and intergalactic scales, do you suddenly run out of ordinary matter? And it seems that that's the other thing that we know about dark matter. It only seems to have a strong influence on very large scales.
Also, since it doesn't interact electromagnetically, it doesn't tend to clump together, so it's harder to find a solid piece of dark matter.
Precisely.
Let's say.
Any more than you're going to find a handful of neutrinos.
So the next piece of news, as I said, a few days ago, NASA announced that ULA is going to be launching the Lucy mission. Lucy is a Discovery class mission. It's a spacecraft set to explore Jupiter Trojan objects. It's supposed to do over 12 years a flyby of 6 Trojans, I believe, and it's supposed to be launched on an Atlas V 401 in 2021. Christian, can you please explain what Trojan bodies are?
Sure. There are, we know that there are a number of asteroids here in our solar system, but there are a collection of asteroids that are kind of caught in a gravitational pocket along Jupiter's orbit. So what happens is that Jupiter and the Sun mutually conspire gravitationally to create these pockets or these wells that are called Lagrangian points. And there are two Lagrangian points, one on either side of Jupiter's orbit, you might say. They're actually along Jupiter's orbit. One is ahead of Jupiter in its orbit around the Sun. The other Lagrangian point is behind Jupiter in its orbit around the Sun. So these two particular Lagrangian points act as kind of like the gravitational equivalent of valleys. Once something falls into that region, they don't naturally accelerate out of that region. So we have these two valleys, these two Lagrangian points in Jupiter's orbit, and so asteroids have collected in there. And these asteroids are called the Trojan, or they're collectively known as the Trojan asteroids. The nice thing about these asteroids is that they're a pretty pristine fossil of the solar system's formation. So studying them is a great way to understand better how our solar system formed.
Just wondering, the Earth has 5 different Lagrange points, like one ahead, right, one behind, and then either side and across from the Sun. So does Jupiter also have? Does it just have 2 Lagrange points ahead and behind its orbit, or does it have all 5?
No, it does have all 5. Yeah. So the 5 Lagrangian points are a feature of any two bodies, in orbit around each other. So yeah, Jupiter does have the 5 Lagrange points, but the asteroids that are classified as Trojan exist in Lagrange points 4 and 5, which I think it's 4 and 5. That's the one that's behind and in front of Jupiter's orbital path.
Okay. Yeah, makes sense.
I also think that there are a few telescopes in the Earth Sun Lagrange points in the Trojans.
You mean the Earth's equivalent of Trojan? I don't know if we have. I don't know if we have spacecraft actually in those particular ones, but we have some others. We do position spacecraft. We have some sun-observing spacecraft near the L1 point between the Earth and the Sun. That's a great place to park a spacecraft if you want to study the Sun. We also put a number of spacecraft, particularly space telescopes, at L2, which is opposite. If you think about the Sun, the Earth, and then L2, way off on the right, that's where we park spacecraft, and that's a great place to be if you want to do, astronomy from a location that is far away from the radiating heat of the Earth. So, yeah, that's where we're going to put things like the James Webb Space Telescope and other space telescopes.
But the L2 point is so far away that if something breaks, we just have to leave it there, right?
Well, yeah, I guess so. I mean, hopefully not. Hopefully we'll have things like the Orion spacecraft or Crew Dragon or Starship or some other maybe Boeing Starliner. I don't know if that's designed to operate in deep space, but if we can ever develop the ability to venture into deep space, that is to go way beyond Earth orbit, then yeah, it is in principle possible to serve as a telescope. However, James Webb is not designed to be serviced by astronauts the way the Hubble Space Telescope is. So, yeah, it's going to be a bit of a challenge when something breaks out there.
Hubble is, I think, the only space telescope that is serviced this way. Is it correct?
Yeah, that's right. There have been other satellites that have been serviced by the space shuttle, but yeah, you're right. The Hubble Space Telescope is the only astronomical facility that was specifically designed to be serviced by the U.S. space shuttle.
That's unless unless you count the Skylab Apollo Solar Observatory, but that wasn't the space shuttle, and it was itself.
Right.
So the next thing we have is a bit of a small one. Ariane 5. We had the first Ariane launch for this year a few days ago. It was a nice launch. It went perfect. They're supposed to have another 4 Ariane 5 launches and a few other. Also, an announcement. If you haven't heard of the Google Lunar X Prize, and that was a competition that was ended, I think, in 2017, in which Google had a reward of $20 million to the first group that will be able to send a spacecraft to the moon, to land on it, and move 500 meters. One of the groups that were a part of the competition was the Israeli Space IL team, and their spacecraft, the now named Bereshit lander. Bereshit is Hebrew for Genesis, the first chapter of the Bible. It is due to be launched as a secondary payload of a geosynchronous satellite on a Falcon 9 rocket. In about a week from now, or a week or two, we will probably stream this launch, and we might also have another video covering more deeply into this tiny lander, the tiny lander that could, hopefully. It's a very interesting one.
Also on space announcements for the near future. March 2nd, hopefully, Demo Mission 1, launched by SpaceX to test their Crew Dragon, will launch. Hopefully. As we have mentioned before, it's Elon time, so you have to add that into account.
I don't think that's Elon time. That's just the space industry. From now on, it's going to be delayed just like a normal mission. Elon time is mostly for ambitious projects like Falcon Heavy and new vehicles, especially. So DIM-1 is going to fly to the ISS and stay there for a few days, just like a normal Dragon mission, but this time with the Dragon 2. The next mission of the Dragon is supposed to be carried out by the same spacecraft. It will be the launch abort mission, in which they'll fly a Falcon 9, and mid-flight they'll shut down the engines, and immediately the capsule should fire its Super Dracos and abort to safety and splash down in water.
I heard that Elon Musk might detonate the booster for effect. I really hope that happens.
I've heard it's supposed to disintegrate and explode itself, because the moment the spacecraft separate, you have just a flat surface on the forward of the rocket, and that's on max Q. So I guess immediately it will destabilize. And if you've seen the first Ariane 5 launch, if you turn 90 degrees in max Q, that's not a good thing, and you will explode.
Right. Yeah, just a quick tangent to the first Ariane 5 launch. The specific details of that failure was due to, what was it called? Stack overflow, where it was, they used the programming for Ariane 4 to put into Ariane 5 in order, it was the same programs and everything, but at max Q, since the Ariane 5 had a different processing center, the data overflowed, and it caused everything to error out, and the entire rocket was destroyed. It was very interesting.
So now I have a few questions for Christian. You worked on the Hubble project, right?
Yes, I did. I worked on the Hubble Space Telescope for a few years.
I have quite a few questions about the Hubble Space Telescope. I know that the Hubble Space Telescope had a few problems when it was first launched. Could you just give us a bit more insight about it?
Well, sure. When Hubble was launched, it as you point out, it was launched with a very terrible flaw, and that was its mirror was ground to the incorrect shape. And by incorrect, I mean to say that Siri. And by incorrect, I mean to say that the mirror's shape was less than perfect by an amount that is about 50 times thinner than a human hair. So it's an extremely tiny deviation from the correct prescription, and yet it was enough to throw up to 90% of the light away from the central source. So if you're taking an image, let's say, of a star, you want to get a nice tiny sharp point of light, and instead what you'd have is a kind of a faint blob of light surrounded by a huge smear of scattered light everywhere. So what we had to, yeah, go ahead.
That little speck of 1/50th of a hairline, that deviation throws off 90% of everything taken by the Hubble.
80, 90%, of the light was smeared out and was otherwise useless. But I say otherwise useless because if the object was bright enough, we could use software to reconstruct what the image was supposed to look like. In other words, we could effectively put that scattered light back into the center and recover a great deal of that information. About 90%, up to 90% of the lost information could be recovered if the object was bright enough. So planets, bright stars, things of that nature, we could still do science, but it was degraded. There's no question about it. So that's why the first servicing mission was really, not just important for getting Hubble back in business, but also for kind of getting NASA back in business. So NASA's reputation was on the line with that mission, and they executed it perfectly. Actually, better than perfect. They actually completed more tasks than they planned to do. So they did a fabulous job getting Hubble back in business.
Yeah, I heard that mission was mainly about just getting some correcting lens, I believe, onto the mechanical correcting lens module on the Hubble telescope. Am I getting that right?
Well, you're right. They were correcting optical elements, but the elements themselves are mirrors. On Hubble, everything's done with mirrors. We don't actually have any lenses. So these mirrors, if the good news about the problem with Hubble's primary mirror, if there is such thing as good news, is that we knew that it was ground to the wrong shape, and we knew exactly how wrong that shape was. So by creating a set of mirrors that were ground to the oppositely wrong shape, they could correct for Hubble's blurred vision, and that would put the incoming light, the raw light, back into focus. So it would really allow Hubble to see to the very limits that optics and physics permit.
So that little, sorry, I lost the word, but that little problem, it was aware before the launch, but they never thought it would be that bad.
Well, they didn't actually know about the problem before launch.
Oh.
At least NASA didn't know. There were a lot of mistakes that were made, that's for sure. So the problem with the Hubble's primary mirror was discovered after it was launched, and NASA was and the scientific community were thinking, okay, what can be done? One idea even suggested, could Hubble be brought back down to Earth and repaired on the ground? The problem with that is that Hubble would be too heavy for the space shuttle to land safely. So launching it via the shuttle was fine, but bringing it back was not an option. So then some engineers realized, hey, wait a second, if we can just deploy a set of corrective optics and intercept the incoming light off the mirror before it goes into the instruments, we can correct the light that way. Now, that was the very first servicing mission. That's actually around the time that I started working on Hubble's, just before that first servicing mission. And then subsequent servicing missions introduced upgraded instrumentation that had their own built-in corrective optics. So eventually, the corrective optics module, which was called COSTAR, was actually removed from the telescope because all of the remaining instruments, all of the since added instruments, have built-in corrections. And Hubble is now operating at really still very much at the pinnacle of its capabilities 10 years after its last servicing mission.
Actually, about the servicing missions, about a week or two ago, I attended to a lecture by Scott Kelly, which is, for those of you who don't know, is a NASA astronaut. He holds the record for, together with Mikhail Kornienko, for the longest duration stay on the ISS. And on his first mission to space, he was the pilot of the Space Shuttle Discovery on a service mission to the Hubble.
Oh yeah, that's right. I forgot which one, but yeah, he was there.
Oh, which one? Yeah, they're twins. Yeah.
No, well, I'm sorry. I meant to say I forgot which servicing mission. There were 5 in total. So.
Yeah, and the orbit, except the Challenger, every orbit has been to Hubble, right?
Let's see. Yeah. Well, I'm trying to think. Was Columbia ever used to service Hubble? I don't think it was.
Let me check that.
It did. The STS-109. That was Columbia.
Okay.
On Hubble.
Wait, wasn't 107 in the last mission of Columbia?
Well, the numbering is the NASA numbering.
Yeah, that was weird. Because 107 was right after 113 and right before 114. Not right before, 2 years before. But they did have 2 years cut in flights because of the Columbia disaster.
Okay. So I guess you're right. Every shuttle except for Challenger.
Oh, yeah. Have you got a story for the STS-125? I mean, I think that's like that mission has a lot of gossip to it, like how it was saved and how was the rescue missions that's gonna go with that.
What was this mission? What was the STS?
It's the Hubble repair mission done back in 2009, and it's famous from around me. So people around me know it as the Hubble mission with the rescue mission plan.
So that was the one with Atlantis?
I think that was the one with Atlantis. Yeah.
I love the Atlantis.
So
yeah.
So have you got like any insight towards what was done to the Hubble at that mission, or just any stories apart from that?
Well, I by that point I had left the Hubble mission, so I myself was not directly working on the Hubble program at the time of STS-125. I do know that Hubble was given the latest greatest suite of instrumentation available, including the Wide Field Camera 3. And to kind of bring our conversation full circle a little bit, the images that were made of the new galaxy that we were talking about earlier were made with the Wide Field Camera 3 that was installed on STS-125. Hubble was also given a brand new set of gyroscopes that are used to help determine its pointing in space. And but as far as the rescue mission, I think you mentioned that earlier. I think that would have been it had some interesting name. It was called STS-800 or something, and it was what was called a launch on demand mission, and they had a second orbiter, a whole stack. I can't remember what shuttle it was. It might have been Discovery. I can't remember, but I think it was all there on pad 39B, and would be made ready to go if Atlantis developed a problem and was not able to land safely. So, yeah, that would have been the first time and maybe the only time that there were 2 full shuttle stacks on the 2 launch pads.
That is an amazing sight. It's just I'm speechless right now.
Well, actually, my own personal anecdote of it is not really very personal, but my wife just happened to be at Kennedy Space Center that day. She was there for doing something involving her work, and she says, "Hey, there's 2 shuttles out there," and she sent me a picture, and I couldn't believe it.
I mean, 2 shuttles on the pad. That's oh.
Hubble a few months ago, I believe, had a problem with its control moment gyros, didn't it?
Yeah, that's right. So as I said earlier, they added a suite of gyros, and ideally, Hubble will have 3 working gyros, so that it can sense. They can sense how it's moving in all 3 axes simultaneously, and use that information to control its pointing in all 3 axes. Well, of the 6 gyros, 3 were there to serve as backup. 3 had failed since 2009, and Hubble was down to what was thought to be its last 3 gyros. And one of those 3 gyros it failed. And it wasn't a surprise. The engineers understood it was going to fail. It had been acting up for about a year, and it failed. And so then the thinking was, well, maybe they'll have to invoke what's called a single gyro mode, and then keep the second remaining gyro as the sole spare backup. Well, long story short, they were able to recover a previously failed gyro, and they were able to get that gyro to work by commanding the telescope to roll back and forth in a couple of different directions, effectively shaking that gyro loose a little bit. And once that was completed, once those maneuvers were completed, the recovered gyro began reporting everything perfectly normally. And now Hubble has been back to 3 gyro mode since the end of October. So a great success on the part of the engineers, and some great thinking when you don't have a shuttle that can go back to service the telescope anymore.
So basically, if you have a computer with some problems, give it a little kick, it'll go back to work.
There you go. Yeah, especially if your computer relies on moving gyroscopes. Yeah.
Kepler ran out of hydrazine, I think.
It ran out of hydrazine years before the gyros failed.
Yeah, that's right. And to be really clear, Kepler had a slightly different problem. We've been talking about gyroscopes, but I want to be clear, because there's the gyroscopes that provide feedback to the central computer of how fast the spacecraft is rotating. So when it's pointing to a new location, the gyroscopes provide feedback. But they actually use a separate set of what are called reaction wheels. And it's these reaction wheels that spin up, right? And then by conservation of angular momentum, if a wheel spins in one direction, the spacecraft has to spin in the opposite direction to conserve angular momentum. So yeah, it was Kepler's. Kepler launched with 4 sets of reaction wheels, or 4 reaction wheels, and 2 of them have failed. And so you're right, they came up with this really ingenious method of using solar radiation pressure to act as that third axis stabilizer. And that gave rise to what was called the K2 mission. So it gave Kepler a second lease on life, but you're right, that did take hydrazine, and that's the problem with fuel. Eventually you run out.
So I believe every space telescope missions have been extended beyond the design lifespan, wasn't it?
Yeah, I think so. I mean, Hubble was only designed to last 10 years. Then they said, well, how about 15? Then 20. Let's see. How many years have we been up now? It will be 29 years.
It's been
this year.
Wow.
Yeah.
Fortunately, we now have tests to look for exoplanets.
Yeah, and so if James Webb ever launches before the year 3000, chances are Hubble can. The hope is that James Webb can launch, and then you can do simultaneous science with Hubble and James Webb, because Hubble is the only telescope. I mean, we have all these space telescopes up there now and more to come, but Hubble is the only telescope that's sensitive at both optical or visible light and in ultraviolet. And that's really important if you want to study high energy objects like newly forming stars and things like that, or the brightest, hottest stars. You need ultraviolet for that, and Hubble is the only telescope that's got that capability currently or planned. So yeah, if they can get James Webb up and keep Hubble going, they'll do it.
Also, a little after the problem with Hubble, I think the Chandra Space Telescope also had a problem. What was that?
Oh, you mean last October when Hubble
Yes.
had problems? Well, Chandra also had a problem with one of its gyros. However, that one turned out to be a much simpler fix. My understanding is that it wasn't a mechanical issue. It was just a software issue. There was apparently a safing event that caused, I think their computer had a restart or something, and it was just reporting bad gyro data. But once they figured out that was the problem, they just reset everything and they were back in business. So Chandra had its safing event the same time the Hubble Space Telescope had a safing event, which was kind of like, great, we got these two aging telescopes that are both breaking down, but thankfully...
Yes, and that was shortly after the loss of Kepler and Dawn. So
yeah, kind of sucked.
That was not a good time.
No.
Unfortunately, as very amazing and entertaining and informative this time has been, our time has run up. I am unfortunately the bearer of bad news, but
you're banned
so.
From the server now.
You always ruin the fun.
Okay, so we were Project Essence. We had as a guest Christian Reddy, was amazing. So please like, subscribe if you liked it, comment. Share it with friends, maybe check out our Patreon and other content, and
be sure to check his YouTube channel, Launchpad Astronomy. The link is also in the description.
And Christian, it's been a pleasure to have you
it
here.
was
A real pleasure.
It's been.
Thank you all very much, gentlemen. I really enjoyed our chat today, and good luck with this show. It sounds like you guys got a really cool thing going here.
Thank you very much.
We hope to.
Thank you.
We hope to chat with you again soon enough when we have a new topic to talk about.
Sure. The universe is a big place. Lots to talk about out there. Happy to do it.